For centuries, the saffron harvest has relied entirely on the stability of local weather patterns in open fields. Iran controls over 90% of the global saffron supply, but decadal climate data reveals a systemic, inescapable drop in production across its primary growing regions. Machine learning models trained on 60 years of historical climate data indicate that increasing atmospheric aridity is the primary driver behind these declining yields. Specifically, the data points to an aggressive, long-term spike in what physicists call the vapor pressure deficit, or VPD. As this atmospheric deficit grows, traditional field cultivation becomes thermodynamically unsustainable. The rising deficit literally pulls the moisture and life out of the saffron corms before they can properly yield. To protect and multiply the crop, agricultural engineers are moving saffron indoors. They use high-density vertical racks inside controlled environment agriculture facilities. Because saffron is the most expensive spice in the world, the unit economics of these facilities require absolute precision. The artificial microclimate must perfectly reproduce the plant's exact physiological requirements. Yet many operators make a critical error in how they manage these indoor environments. They rely on the flawed metric of relative humidity to dictate their climate control. Achieving maximum indoor saffron yield while avoiding catastrophic crop failure depends on facility operators abandoning relative humidity and adopting vapor pressure deficit as their primary operational metric. Relative humidity measures the amount of water currently in the air compared to the maximum amount that air can hold. Because that total capacity fluctuates with temperature, using the percentage alone is a poor predictor of plant water loss. The exact thermodynamic rule of air is that its water-holding capacity roughly doubles with every 20° Fahrenheit increase in temperature. Consider a standard indoor data scenario. If we hold the relative humidity completely constant at 70%, but increase the temperature from 60 to 90 degrees Fahrenheit, the total water-holding capacity expands drastically. It still contains 70% moisture, but the physical gap to total saturation has grown. This empty gap is the physical pressure deficit. Here, the absolute deficit increases from 0.55 to 1.45 kilopascals, despite identical relative humidity. Vapor pressure deficit is defined explicitly as this absolute difference between the air's current moisture and its maximum saturation point. It represents the literal atmospheric suction force. VPD is the thermodynamic thirst that drives water and nutrients out of the soil, through the plant's xylem, and out of the leaves. A saffron corm requires active, dynamic modulation of this suction force across its different developmental stages to yield a successful harvest. This chart maps the standard horticultural vapor pressure deficit matrix, outlining the safe operating kilopascal zones based on temperature and humidity. During the early propagation and corm stages, operators maintain a low VPD of 0.3 to 0.4 kilopascals. Maintaining this low gradient prevents the young corms from drying out, which also reduces the need to constantly water the substrate. As the corm enters the vegetative stage, the environment must pull harder. Operators push the VPD into a moderate range of 0.4 to 0.8 kilopascals. This increased atmospheric pull drives the heavy transpiration rate, moving nutrients upward to build the biomass required for a flower. For flower induction, the temperature is dropped to between 18 and 22 degrees Celsius, and the VPD is tightly controlled between 0.7 and 0.9 kilopascals. This stage ensures the plant can transpire and cool its canopy, avoiding an atmospheric pull that structurally damages the delicate stigma tissues. Engineering this shifting gradient aligns the room's environmental suction force with the plant's changing biological priorities. Failing to maintain these precise kilopascal boundaries results in immediate physiological breakdown. At an extremely high VPD, anything over 1.5 kilopascals, the atmospheric suction becomes so aggressive that the plant loses water through its leaves faster than its root system can replace it. The plant initiates an emergency response mechanism. It forcefully clamps its stomata pores shut to prevent total dehydration. Once the stomata close, biological progress halts, photosynthesis stops, vegetative growth stunts, and the plant restricts the synthesis of crocin and safranel, the phytochemicals that give saffron its value. This state of extreme microscopic stress is the mechanical failure that climate models show destroying outdoor saffron yields worldwide. The opposite extreme is equally destructive. If the vapor pressure deficit drops to near zero, under 0.3 kilopascals, during the late growth stages, the system fails. At this level, the air is near saturation. The transpiration gradient collapses. The plant cannot evaporate water, causing moisture to pool heavily across the canopy. Zero nutrient flow in a heavily saturated environment creates a perfect breeding ground for aggressive fungal pathogens to rapidly multiply. A collapsed VPD invites specific invaders like Fusarium corm rot, Penicillium blue mold, and Sclerotium white mold to overtake the crop. Relative humidity only tells an operator what the air holds. Vapor pressure deficit dictates exactly what the air does to the plant. By engineering precise vapor pressure deficit stages inside a controlled environment, facility operators can bypass macroeconomic climate limitations and maximize the biological efficiency of the world's most valuable spice.